Hi everybody! Today we are going to be talking about simplifying trig expressions. Before we begin, I just want to give you a disclaimer. I personally think this is the most fascinating of all of the units that we're going to be doing in pre-calculus, and I think some of you guys are going to find it interesting as well. However, it can also be challenging if you don't start off on the right foot. So make sure you're staying caught up and don't try to memorize everything. Instead, one of the things that you need to do is to try and wrap your head around how these things are working and why each one of the identities is what it is. And if you keep that in mind and you see the procedures and the strategies that we're going to be using to simplify, I think that you're going to see that this particular unit makes perfect sense and is beautifully logical. So here are some of my strong beliefs about this unit. Seeing the beautiful and elegant underlying logic behind the identities is going to make this much more interesting. We're going to learn several dozen identities in all, and very few students would ever be able to effectively memorize all of them, myself included. If you clearly understand why these identities work, you're also going to see that they're all interrelated and that the relationships between them are going to help you see this as a single united subject rather than a whole bunch of useless and random facts. So not only is memorization a totally boring way to approach mathematics, but just simply memorizing dozens of formulas that don't make any sense isn't going to help you when you get into calculus and when you're going to actually have to apply them. Hopefully you'll be able to keep these things in mind as we begin this unit, and here we go. Today we're going to talk about the beginning of Unit 3, the fundamental identities of trigonometry. So let's start. What's an identity anyways? It's basically just an equation that's true for all values of a variable within the domain. In order to verify an identity, we'll start by simplifying one side of an equation to show that it's equal to the other side. Usually we try to only manipulate one side or simplify one side. We can do that by using trig identities and lots of other skills that we've learned along the way. Often there's more than one way to simplify an identity. So if you are working on one method and your neighbor's working on another, it doesn't necessarily mean that you're wrong. Both pathways could get you to the same final verification. We're going to start today by just simplifying identities so you can see how this all works. So some procedures to have under your belt before we begin. Do not skip steps. Try and work on only one side of a given equation, if an equation is even given. Make sure you're working down your paper, so work vertically, not horizontally. If your work cannot be followed, it's not going to be marked correct, so make sure you're not skipping steps. Going on back to that first one. And you are not done until the side you're working on reads exactly the same as the other side, if this is an equation. So here's some strategies that I've used as I've done a lot of simplifying trig expressions. I like to start off by trying to choose the more complicated side to work on. I like to put everything in terms of sine and cosine if I have other trig expressions. Try and factor. Sometimes that can make something pop out. If you've got fractions, try combining them. That's a great step in order to start simplifying. And then also try and multiply the numerator and the denominator by the same factor. Let's begin by talking about the first set of fundamental trigonometric identities. We'll start with the reciprocal identities. These are actually ones you probably already know. So we know that sine of x is equal to 1 divided by cosecant. And that means that cosecant is also equal to 1 divided by sine. They're reciprocals of each other. Similarly, we have the reciprocal identities for cosine, secant, tangent, and cotangent. Next, we have the quotient identities. The quotient identities are for tangent and cotangent, because tangent and cotangent can also be written as a fraction that divides sine and cosine. So tangent is our sine value divided by our cosine value, and cotangent is our cosine value divided by our sine value. Now, knowing these identities, we can put them all together and we can simplify some trigonometric expressions using substitutions. And that's the name of the game, you guys. We're going to be substituting and simplifying, substituting and simplifying. So try and keep that in mind as we work through the next couple problems here. Here's our very first problem. We're asked to use those basic identities to simplify this expression. Now it looks kind of crazy, right? Look at all these trig functions all being multiplied together. But I'm going to use one of my very favorite strategies, changing everything into sines and cosines. So let's go. I'm going to start with sine. I don't need to change sine because sine is already sine. It's being multiplied by cosine. Also, I don't have to multiply or change cosine by anything since it's already cosine. Remember, I'm using the strategy of changing everything into sines and cosines. Whoa. Here's tangent. I'm going to go ahead and use one of my quotient identities to change tangent into the fraction sine divided by cosine. Again, next we're multiplying by secant. I'm going to go ahead and use my strategy of changing everything into sines and cosines, and I'm going to change secant into 1 divided by cosine. That's its reciprocal trig identity. Next, I'm going to change cosecant into, you got it, 1 divided by sine. So this is how we apply that strategy of changing everything into sines and cosines. Now, I've used my identities, I've substituted, and now I'm going to simplify. As you know, any number divided by itself is 1. Any number divided by itself is 1. And after simplifying, I can tidy this up, and I have a sine times 1 in my numerator, and I have a 1 times cosine times 1 in my denominator. Now everything is in sines and cosines, but I'm looking at this and I happen to notice that sine divided by cosine is tangent. So I was able to simplify this crazy expression and turn it into a single term, just plain old tangent. And that's how we simplify trig expressions. So that was kind of fun. Let's try another. We got a few more cofunction identities for you. So the cofunction identities look like this. And it basically says that if we take the sine of, in this case, pi over 2, which you know is 90 degrees, and we subtract some angle theta, that result is the same as the cosine of that angle theta. So sine and cosine have this cofunction identity. And so we can add these to our arsenal along with those basic reciprocal and quotient identities to use as our set of substitutions. So let's continue. Let's try them. I would say that probably the sine and cosine cofunction identities are the ones that are used most frequently, but a good rule of thumb is if you see a pi over 2 in the problem, it's probably likely you're going to be trying to use one of these cofunction identities. So here's one for you. We're supposed to use these identities to find the value of this expression. So one of my favorite strategies, as I've said, is to change everything into sines and cosines. So I'm going to continue that strategy here. I know that secant is really 1 divided by cosine. So I'm going to use substitution, and I'm going to replace my secant with 1 divided by cosine. That's my reciprocal identity. And it's getting multiplied by the sine of pi over 2 minus theta. If you recall from our cofunction identities, the sine of pi over 2 minus theta is really equal to cosine. So I can use that as a substitution here. So instead of writing sine of pi over 2 minus theta, I'm going to write cosine of theta. Now, that is a whole number, but I can turn it into a fraction by dividing it by 1. And hopefully you can see here that any number divided by itself is 1. So overall, this whole expression is actually equal to 1. Pretty cool, huh? It looked so crazy, and then there it was, just equal to 1. All right, so we've got some more identities that I'm throwing at you. We've got these even and odd function identities. So in order to be an even function, if you substituted a negative x value into the function, you would actually get the same result as substituting in a positive of that same value. For an odd function, if you substitute in a negative value, then the result would be what you would get if you substituted in the positive value with the result multiplied by -1. So what this means is that cosine and secant, which are even functions, they have that symmetry across the y-axis. When we substitute in a negative value for x, the result is the same as if we would have substituted in a positive number. Now, sine, cosecant, tangent, and cotangent, they are not symmetric about the y-axis. They actually have diagonal symmetry, or we call that an odd function. And so these functions, when we substitute in negative x to the argument, the result is the same as if we had substituted in a positive x and then multiplied the whole entire result by a negative. Now, I just basically think of this as moving the negative to the outside. So out of the argument and moving it to the outside. And these, since they're the same, the negative doesn't really matter. The sign in the argument doesn't really matter. So let's apply these basic trig identities. So sine is sine. I'm using my strategy of changing everything into sines and cosines. So the sine of theta is the sine of theta. Now, cosecant of negative theta. This is not saying cosecant minus theta. After your trig ratio, it always comes the argument, which includes your angle. So this is the angle. It's negative theta. Cosecant is an odd function. And if you don't recall, we can bring it back here. So cosecant is an odd function, which means that cosecant of negative angle is the same as a negative cosecant of the positive angle. So I'm going to use that substitution here. So instead of writing the cosecant of negative theta, I'm going to multiply, since these are being multiplied together, I'm going to multiply by negative cosecant, cosecant, I started writing the word out, negative cosecant of positive theta. And I can actually simplify this a bit further because I know that cosecant is really 1 divided by sine. So then this says actually sine theta times -1 over sine. Remember, the negative is getting multiplied to the cosecant, and since cosecant is really 1 divided by sine, I could write it like that. I could turn sine into a fraction, and then I'll reduce. So any number divided by itself is equal to 1. So my final result is 1 times -1, which is -1, and 1 times 1, which is 1, aka -1. Looked a little weird, but we were able to figure it out. So let's try this one. Example number 4 asks us to use our basic identities to change the given expression to one that involves only sines and cosines. Ooh, my favorite strategy. Then simplify to a basic trigonometric function. Okay, so just like what we've been doing, just with a lot more words in our directions. So let's follow the rules. Cosine is already a cosine, so I don't need to change it. just going to start with cosine. Minus sine. Okay, we're doing good so far. Now this term is cotangent times sine. I know that cotangent is really cosine divided by sine. So I'm going to use that quotient identity to replace cotangent with cosine divided by sine. And then it's getting multiplied by sine. Well, I don't need to change that. Since I'm multiplying it by a fraction, maybe it will be better if I put a 1 underneath. And lastly, oh, you see what they've done here? A cofunction identity. Remember, you see that pi over 2? You're thinking cofunction. So the sine of pi over 2 minus theta is the same as cosine. So I'm going to put plus, because we have an addition sign here, plus cosine. Fantastic. So let's simplify this up. Any number divided by itself is 1, so we can reduce these signs. And I'm now left with cosine theta minus, well, this is cosine times 1 divided by 1. That's just cosine. Whoa. Plus cosine. And just like any regular math problem, cosine minus cosine is 0, and 0 plus cosine is cosine. So this whole expression simplified down to just a plain old cosine. And we're done. Alrighty, we have one last one here. So we can actually use factoring in order to simplify as well. So I'm going to use factoring to solve this problem. I've got in my numerator cosine squared minus 1 divided by cosine plus 1. In the numerator, it's written kind of like in the form something squared minus something else squared, since we know that 1 is really 1 squared, right? And this is a difference of 2 squares. A difference of 2 squares can be factored rather easily. You take the square root of your first term, the square root of your last term, you write 2 factoring parentheses with them, and change the signs in the middle. Of course, you can use any of your factoring strategies that you may know to factor this, but this is basically the pattern that a lot of people use. So let's go ahead and rewrite this using factoring. Cosine squared minus 1 is a difference of 2 squares. So I'm going to start by factoring the numerator. That's going to give me cosine plus 1 times cosine minus 1. And down in the denominator, I have the whole expression, the cosine of x plus 1. Now, any number divided by itself is equal to 1, even if that number looks like, you got it, an expression. The cosine of x plus 1 divided by the cosine of x plus 1 is equal to 1. Any number divided by itself is equal to 1. This leaves us with the expression left over after simplifying, the cosine of x minus 1. And that, my friends, is our final answer. So that's what I have for you today. It's our introduction to simplifying trigonometric expressions. I would go back and write down some of those basic trig identities, especially the ones you don't already know, perhaps those cofunction identities, or maybe even the even and odds. And that should help you with the upcoming lessons in this unit. I hope that that was enjoyable and comprehensible, and that you guys enjoy this unit, the analytic trigonometry unit, as much as I'm going to enjoy teaching it to you. Have a great night. Bye-bye.